From January 2012 to July 2012, he was with the C.R. Rao Advanced Institute of Mathematics, Statistics and Computer Science. Since August 2012, he has been a faculty member with the Indian Institute of Information Technology, Design and Manufacturing, Kancheepuram, and where currently he is an associate professor. Also, he served as an associate editor for Elsevier's Computers and Electrical Engineering Journal. Also, he is a senior member of IEEE. At present, he is serving as Dean, Sponsored Research, Industrial Consultancy and Continuing Education in IIITDM. His research interests include different aspects of wireless communications with emphasis on cooperative diversity systems. Without any further ado, I invite the speaker to take over the session. Over to you, sir.
Okay, so good morning, one and all. So the second session we are going to start. The second session, before we are starting, some information I would like to share. See, totally, as I said, we have 14 sessions, and the last session, 15th session, is allocated for the valedictory. So all these 14 sessions we have planned in such a way that we cover all the fundamentals of the machine learning and the fundamentals of the 5G mobile wireless communication. So it is essential for the participants to understand the fundamentals first, then they can build on the applications. So this entire FDP is planned because it's a preliminary level FDP. There are two levels which AICT suggests. One is a preliminary level, another is the advanced level. So the preliminary level of this FDP, it is planned to cover all the required technologies or fundamentals to understand or work in this research area. And later on, the advancements, algorithms, level advanced things we can think of. But now the primary focus is to give the fundamentals required. So therefore, we included all the important 5G technologies like NOM, fundamental like cooperative is one session, NOMA is another session, spatial diversity, VLC, that is visible light communication. So all schemes we have covered. On the ML front, we have all the fundamentals will be covered by an industrial expert. So we are going to have a right blend of the fundamentals and advanced concepts. There are two applications of the ML. One is on wave processing, another one is for the video surveillance. That will be given by the ML experts. That two talks is on application side. So that is altogether about this workshop. So let me start giving you the overview of the 5G mobile networks. And this session is going to be a fundamental session for all other sessions. If you want to understand all other sessions, this session is essential. But why this session is planned with fundamentals is the participants are from both computer science background and ECE background. So therefore, for ECE background participants, the ML fundamentals are required, and from the computer science, these mobile communication basics are essential. So though they have studied some elective courses here and there, and might have handled some courses for the interdisciplinary things, but still it is better to start with the fundamentals. So therefore, this session is going to focus on the fundamentals of the 5G mobile networks. Okay, fine. Let me start the session and go slowly into the concepts. So I hope the screen is visible to all. So the overview of the 5G mobile networks we are going to start. So before starting this, let me start with the history, because what our forefathers did is very important, so that it will help us to invent new things. Okay, we cannot keep on reinventing the wheel every time, right? So in the research, what is new is very important, and the literature survey plays a significant role, because you cannot keep on telling the same information. So therefore, the new addition of the new information is essential for the research community. So let me start with my own favorite researchers. So I just listed out, there are many significant researchers who work in this field, but I just listed some of the very known and my personal favorite researchers today who are related to this mobile communication and wireless communication in general. So let me start with the electromagnetic theory. It was given by the James Clerk Maxwell. So Maxwell's contribution is very enormous in the electromagnetic field. Though there was a contributions earlier by the Faraday and Ampere, and even they conducted some experiments and proved the existence of magnetic waves. But the existence of the electromagnetic wave was theoretically proved by the Maxwell. That is why he is called a father of the electromagnetic field. So he has done excellent research in the year 1864 on the electromagnetic theory and came out with the 27 expressions. And later we just read the reduced form in both the differential and integral forms. That four reduced expression what you read is in the both the differential and integral form is a reduced form of those 21 expressions, and his contribution is very significant the electromagnetic fields. And later the radio waves, the existence of the radio waves is proved by the Henry Hertz, and still the concept of the frequency is very interesting. See, all the signals exist in time domain, right? So when suppose a baby is crying, okay, if you see that is a time domain expression. The amplitude is varying with respect to the time, and I am speaking. If you see my speech, it is the amplitude versus the time. Okay, with respect to the time, different amplitudes. That is how you understand the language. That is how we pronounce the words. So, but the Hertz has given a very interesting uh, dimension to the time is a frequency, and the existence of the radio waves was proved by this Henry Hertz, and this contribution is very significant. The radio communications, and later parallelly in the wireless communication, how these two people are involved. On the side, other side, in the wired communication, an important invention happened, or the groundbreaking research has happened from the Alexander Graham Bell. Okay, so this Graham Bell has invented the telephone equipment, and he demonstrated the wired communication between the two places, and that was a groundbreaking, and many people started to communicate with each other. Earlier the communication is only through persons or through birds, but after that people started to speak through the telephones. That was a wonderful uh, contribution. And also AT&T Bell Labs has contributed a lot in the thing, especially the binary frequency shift keying was first used for the digital telephony. Later we moved on to the pulse coded modulation. And later, again in the radio communications, the wireless side, the Marconi has invented the radio equipment. So he transmitted the radio waves across Atlantic Ocean, Atlantic from one end to another end, and he invented an equipment to receive the radio waves. So that was a beautiful invention by the Marconi, and later people to broadcast their information over the air with the help of that equipment. And in 1906, the first radio broadcast has happened. Obviously, it was an amplitude modulation only, and with a double sideband full carrier, it was transmitted. In the year 1918, the concept of the super heterodyne receiver came. The concept of the super heterodyne receiver was like we have audio frequency, we have convert to intermediate frequency, and from there we'll just amplify and do this required signal processing, and then again we are up converted into the RF front. So the radio waves will be transmitted from the RF antenna. This mixing of the two different frequency is a heterodyne concept, and this super heterodyne receiver is invented by the Armstrong. Armstrong is also invented another indirect method for the frequency, indirect method of generating the frequency modulated waveforms. That also an important contribution of the Armstrong, and that is how we enjoy nowadays all these FM stations we are enjoying. It is all because of the contribution of the Armstrong, and we can use the FM modulation both for the toys. In the toys also we can use the FM modulation to wirelessly control anything or to wirelessly transmit anything. We can use a frequency modulation. But the challenge with the FM is that 88 megahertz to 108 megahertz, that frequency band is licensed band. So therefore, without the permission of the government, you cannot operate that bands. Therefore, people they want to wirelessly operate anything, they go for the ZigBee. ZigBee is for the short range wireless communication. Therefore, people prefer most of the toys which we operate wirelessly, either through sensors or either through this LED sensor, optical, I mean free space optics, optical communication through the infrared LEDs. That is one thing. For that, line of sight is required. But for only using the radio waves, we can go for the Zigbee. Another idea is the Zigbee is sufficiently you can operate within the room. Suppose your room size is available or a big hall, you can operate using Zigbee. Suppose you want to narrow down the field, I mean very smaller field, say within a meter or 2 meters, then we can go for RFID technology, radio frequency identification technology. You can use the RFID tags. So that is for the near field communication. That is also nowadays the credit cards use a near field and far field communication. You don't have to insert your credit card to check to read the chip which is embedded in the card. Just you can just tap the card so that the RFID technology will work and it will recognize using the near and far field technologies. And next, another significant research is the Nyquist contribution. The Nyquist has came out with the sampling theorem that is very interestingly known as the sampling frequency can be greater than or equal to twice of the maximum frequency component of the signal. So that means Fs is greater than or equal to 2Fm. That was a Nyquist rate and Nyquist sampling theorem that was playing a very important role in converting the analog signals into the digital signals. So that is the important contribution. Later on, we have the quantization, we have the encoding, but the first sampling process is very important so that we can avoid the aliasing noise at the other end. So that was the idea which is given by the Nyquist. If you follow the Nyquist sampling theorem and also use a pre-alias low-pass filter, we can significantly reduce the aliasing noise and convert the analog signals into the digital samples. And later on, in 1937, the pulse-coded modulation we have invented. So therefore, the analog communication, we can, with the help of this pulse-coded modulation, I can replace the conventional analog communication telephones to the digital telephones. That was possible with the help of the pulse-coded modulation. Though, as I told in the previous slide, AT&T Bell Labs initially tried with this binary FSK with the mark and space frequencies, the binary FSK they have used. But the problem is with this, we need too many frequencies. And the electromagnetic spectrum they don't want to utilize, therefore they shifted from the FSK to this PCM, pulse coded modulation. And 1948 is a year for the communication theory, and the father of the telecommunication, the Shannon, came out with an excellent paper, Statistical Theory of Communication. He has proved what is the capacity of a wired and wireless communication for the AWDM channels, especially for wired communication is proved for the AWDM channel. Later on, the Shannon theorem has been developed for many other systems like faded channel, everything. After the invention of this pulse-coded modulation, and people understood the Shannon's theorem and started to explore the full capacity of the channels, and they came out with a TN system. And the TN carrier was typically 1.544 Mbps speed. Okay, that was the initial speed. The basic one wire can carry 1.544. That means typically it can carry 12 voice channels, and each channel is of 64 kbps speed. And how this 64 kbps has come means, suppose we have the voice, and the human voice is basically 3 hertz, I mean 300 hertz to 3.4 kilohertz. If you maximize it, maximum we will have a 4 kilohertz. That is allotted for the telephone voice channel. So 4 kilohertz, and if you apply the sampling, so we need the sampling frequency is Fs is equal to 2 times Fm. Fm is the maximum frequency component. So the maximum frequency component is 4 kilohertz. So Fs is equal to 2 into 4, 8 kilohertz. And each sample, so this Fs is the sampling frequency. So each sample, if I represent using the 8 bits, so that means 8 bits required to represent each sample. Then the calculation is going to be 8 into 8, 64 kbps. So that is the 64 kbps, and 12 we will get this 1.544 Mbps. That is a T1 carrier which was used. Then from onwards, for so many decades, people were using this successfully to transmit the signals. On the other side, computer network side, we came out in the year 1943 to 46. We came out with the first electronic digital computer, which is very huge size. The room size of the computer was invented, and later this ARPANET was invented by the American Army. And the year 1985, the internet evolved, and after that there is a slowly, people started to expand the local area networks. The first local area networks picture you can see in the, which I shown it, the people we used, even we used to sit in those days in the lab, the local area networks. And the wide area networks has very limited capability. Earlier with the dial-up modems, using the telephone cable, we just try to get the internet from the telephone cables, and the speed is terribly low, and we cannot simultaneously use both the telephone and internet. So the moment you use a telephone, the data is cut, because we were using the same channel, integrated channel, both for voice as well as data. So I can use only one at a time. That was the earlier, been starting 1996. I remember very well those time, when our professors were using this internet, it was like that. And later, there are many people like Yahoo and people came, and they just developed this world wide web to a greater deal. But now we have everything in the internet, and all the information now is available. If you open the YouTube, or if you will get all kind of users information. Facebook for emotions, and Twitter for quick text messaging, and we have other tools to share our emotions. And for video calling, we have the WhatsApp, Skype, lot of things has developed in this www. Fine. Now let me come to these technologies. Like start from where now we are in 5G era, and up till 4G we completed. So what has happened is from the 1G to 4G? That is what the next thing. So I just classified. There are many more data. A lot of data are available in internet. So let me start with the first thing. The first mobile is called the first generation mobile technologies. The first generation mobile phone sample is shown in the picture. In the period 1980 to 1990, it was approximately, I put the year, it was 1980s to 1990s. We were using the 1G mobile technologies, and the technology was completely analog in nature. It is like your FM channels. Okay, I just have this large amount of bandwidth. I just divide the bandwidth into a smaller subcarriers, and each user was allocated a subcarrier. And the user once uses a subcarrier, the other users cannot use it because it leads to the interference. And there was, in olden days, there was no MIMO and all that concept. Only one carrier per user, and therefore the total number of subscriber is very limited in the wireless domain. Okay. Whereas telephone, it has got in public switched telephone network (PSTN), it has got a huge number of subscribers. But here in wireless domain, we have this limited subscribers because of the allocation of the limited number of subcarriers. But it was integrated with the PSTN. That was a beautiful thing which has happened in those days. It is the mobile technology was not like aloof. So you can make a call from your mobile phone to the PSTN. That means public switched telephone network. That means your telephones, any telephone you can call. And from the telephone, you can call the mobile phone. That means that integration was made in those days. And earlier in 80s, there was another concept which came out along with that, though it was analog. But that time, people came out with the ISDN, Integrated Services Digital Network. That means an attempt was made to integrate all the services like voice, text, voice, and video, image, all the things they want to put together. They attempted it, but the availability of the channels was limited initially in the ISDN. Later, they developed to a broadband ISDN concept. Okay, and they choose an asynchronous transfer mode as a switching technology to implement the broadband ISDN concept. And this, the synchronous optical network or the synchronous digital hierarchy, that was used as a backbone network. So the SONET was the backbone network, and ATM was a switching technology. With this, they want to implement a broadband ISDN concept. But because of their business and other things, it was not taken up that respected. Therefore, people were very happily using the 1G mobile phones. And this application, the bandwidth was very limited, like 30 kilohertz analog signals only. And the main application was only for voice and the poor quality. But those days it was sufficient enough because the number of subscribers were very limited. Later, people moved, I think we all moved to the 2G mobile phones. When the 2G mobile communication came, that is the GSM, the global system for mobile communication came, everybody, almost many people started to use. I also started to use the GSM phones. I purchased, I think, in the year 2009, 2003 or something, I purchased my first mobile phone, and there onwards I was started to use the mobile phones. And those days there was a charges. There was a we need to pay money both for incoming as well as outgoing. So whether somebody is calling you, that is incoming, and still you need to pay for that. That was a time I am even for the charges for the SMS was also there. And before that, this mobile communication came, people used pager devices. The pager is only for the text services. Only you can read. If somebody sends a message, you can read and you can resend the message, or you can reply to the persons. So that was only for the text. But somehow the pager RPG introduced a pager in India, but still it was not that popular because people did not understand the business and other things with pager. But 1G didn't pick up as Dr. Sai Dheeraj told very clearly. 1G we were very much lagging. We didn't pick up. But 2G we picked up well, and we used a lot of 2G mobile phone. As a resultant, the company is ready to invest, and lot of base stations came, and even it reached almost all the cities very well. And the technology which was the combining technology which was used is time division multiplexes. That means each carrier frequency was time shared between 6 to 8 users. In India, we were using 6 users, and there are some countries which were using 8 users. So that means one carrier frequency in first 1G, one carrier frequency was used by only one subscriber. But now this one carrier frequency is used by the 6 users simultaneously in a time shared fashion. That means all the users will be using. So the moment same carrier frequency is used for the 6 mobile phone conversations. But it is like, we use a time division multiplexes. That means each user will get a fixed time slot to talk. But the users will not experience any delay because the time delay from switching over from one mobile user to another mobile user is in the order of microseconds. Okay, therefore, people doesn't feel that delay. But still, it was efficient when compared to the 1G because we are able to, get more subscribers. That means 6 times more subscribers than the 1G. The frequency band is also there are dual band. I think we all use the dual band, and there are some countries which use quad band 2G communications. And means they were using 4 different bands. But in India, we were using the dual band 2G mobile phones. That is, one is on 900 megahertz and 1.8 gigahertz. This 900 megahertz also slightly used for the cordless mobile phones. That means it is a PSTN based mobile phones only between the subscriber loop in this not even subscriber loop. It is between the subscriber terminal equipment and to the this subscriber receiver unit. That link alone it is like wireless. That is a cordless phones. Okay, that also operating around 900 megahertz only, but there were people don't feel that difference because of the limited number of subscribers. We were very happily using the 2G communication. But the main problem with the 2G is the data rate was very low. It is 64 kbps only, and the bandwidth is 25 megahertz limited, and it is only used for those days only for the voice in 2G. And later we extended the small messaging service SMS, that is for the text application along with that. So we went for entering standard called 2.5G, which is supported with the edge technology. Edge means enhanced data rates for the GSM evolution. So which was supporting both voice as well as text, and people were very happily using the 2.5G. Okay, and people never bothered about video calling, all that. People never bothered. We are very happy with the 2.5G, and because the main thing is why people were happy is the mobility. Using mobile phones, the conventional telephones don't give that mobility, whereas these people have a mobile phones, they move anywhere, and they were able to talk. Though there were roaming charges because of this, constraints with the frequency and the electromagnetics, we explore the limited spectrum of the electromagnetic spectrum, EM spectrum. Therefore, the charges also were there for roaming. That means whenever you move from one region to another region, you have to pay charges to them. And there was a problem with the handoffs. That means handoff means how you switch over the mobile call from one base station to another base station. That is handoff. And people had faced, the calls were shut down or terminated and faces the poor quality of service because of the kind of problems. And when they are making a new mobile calls, there also they had a problem of the call dropping probability. Okay, there are one is called call blocking probability, another one is called call dropping probability. Those days people, so whenever a new call is made and they will not be able to connect to the another subscribers immediately, they have to keep trying one or two times because the base stations were having a limited number of carriers, and the carriers it will be given to one subscriber to another, and when the subscriber database increased and they couldn't handle it more, and later people invented the CDMA. The CDMA, the beauty of the CDMA is it can handle the huge number of subscribers. Why? The code division, because of the code division multiple access. And that means one carrier frequency can be used simultaneously by 64 orthogonal users. Okay, that means each user use a codes, orthogonal codes. So one carrier, see, note down, in 1G, one carrier, one user. 2G, one carrier, 6 users can use simultaneously. In 3G, one carrier, 64 or 128 orthogonal users can use simultaneously. See how many subscriber that you can handle simultaneously. So therefore, the 3G were comfortably handling large number of subscribers. Okay, and that frequency is also, that carrier frequency is also 1.6 gigahertz to 2 gigahertz. Still, we were operating in the less than 3 gigahertz band. We were operating, and the bandwidth is also increased to 100 megahertz. Therefore, along with voice, we can try out with text, video options also, but with limited quality. Okay, the videos were not that we cannot make a very video calls or all that, but only advantage is like you can stream the video. The streaming videos are possible. Another thing is we can download the videos with a limited capability, I mean low data rates, and the quality is also low. And interactive voice and video also people attempted using 3G, but only because of the WaveDM. WaveDM allowed the interactive video things. Because earlier, suppose the huge data file is available, to directly put that huge data thing to the channel directly, that undergoes a heavy frequency selective fading. Later we are going to see what is that frequency selective fading. But this orthogonal frequency division multiplexing is divide those information into smaller small bands, and each subcarrier is allotted one small band of information is allotted. So therefore, what we did is we did a trick. That means the signal bandwidth, that means the bandwidth of the signal is lesser than the coherence bandwidth of the channel. Like that, we made an arrangement using the orthogonal frequency division multiplexing. Therefore, the huge videos can comfortably go into the channels, and we are able to get a good quality of service using the WaveDM. Therefore, the application, the interactive video was possible with the help of the WaveDM. That was the 3G mobile technology. And the data rate is not very great, but still we were comfortably getting this 2 Mbps. That means 1.7 Mbps. Even some operators, they were operating on 6.2 Mbps. When you buy the 3G dongles, you can read 6.2 Mbps it can support, and 3G were supporting the Wi-Fi connections also. So those were all the things, and there are many vendors came into the market. Start from the till 2G, the Nokia was the primary, vendor for the mobile phone things. But later there are many competitors came. Samsung is one of the great competitor to other things, and because they were started to introduce this Android OS, the tiny OS, they started to introduce. As a resultant, the people can have a very, good guide. That means the graphics user interface was great, and people were easily using their mobile phone for multiple purposes. So that was another thing. The Android invention was another thing. Though there are other OSs, KitKat and other OSs, the Android was very superior. Though there are other OSs by the Apple and other people, but this Android was used by most of the vendors. That was another thing. And later, the 4G mobile technology, which we are using 2010 onwards, the 4G, we are very happy with this the data rate which is supported by the 4G, because 100 Mbps data we are able to get in our mobile phone, and we are making the voice, video calls directly to whoever the person, I mean, wherever they are in the US or any continent. So the continental to continental calls are made very easily, and the latency was very low. Latency is this delay, and the overall delay is called latency, which includes the propagation delay, which includes the switching delay, which includes other delay components. But the overall latency was very low. Therefore, we are able to comfortably talk with other person through the videos, and we are able to connect with the Wi-Fi also. The Wi-Fi was operating different thing. Therefore, the mobile phone become like a multi-radio and multi-band. Like multi-radio means the mobile phone can operate the Wi-Fi, either it is a 2.4 gigahertz or 5 gigahertz bands it can support. That Wi-Fi, either if it is 2.4 or 5 gigahertz, both the bands the mobile phone supporting. And the Bluetooth 2.4 gigahertz, Bluetooth it was supporting. And then on the other side, the FM radios, it has a FM 88 to 108 megahertz, that multiband. And in the mobile communication itself, it can support 2G, 3G, 4G. So these multi-band is also it can support. So the mobile phone become like a multi-radio and multi-band. And it has got a very fast processor we were using. And the Qualcomm is excelling in in manufacturing the fastest processors. Drag and Scrap. There are many fast processor and with a higher RAM. Now the mobile phone itself coming out with a 6 GB RAM. Okay, earlier we thought of 6 GB RAM only in computers or laptops. Now the laptops and computers are upgraded to 64 GB RAM. Nowadays we use 64 GB RAM for our laptops and this system. Earlier those RAM were used only for workstations. So see the development. It is all because of the development in the wireless domain. Sorry, in the both wireless domain as well as in the VLSI domain. In the microelectronics, a lot of things has happened. Now we have, the nano chips are available. So therefore, the miniaturization. The miniaturization is that devices becomes very small. Therefore, we can accommodate all these things. And there are a lot of development in our technology also. That is why we are able to have the multi-band and multi-radio in a very smaller size. And people even now this Wi-Fi routers, Ticona and other companies like ATAL, Ticona, they were started to use 8x8 MIMO onto their devices. And those 8x8 MIMO things is supported by our mobile phone. You can connect a mobile phone with those Wi-Fi routers. So that is the technologies keep growing. So the long-term evolution as standard of the 4G mobile technology has came out with a lot of supports. And with respect to the 4G, there are many more things to talk about the 4G, but I'll just wind up the overview point with this. Later, we'll take up technologies one after another. There we'll go for comparisons. And coming to the 5G technology, so 5G standard has not yet come, but all the vendors are now releasing 5G. Ericsson is come out with excellent things, a lot of materials, and Samsung. Every vendor has come out with a lot of things. And other things, standardization bodies like International Telecommunication Union came out with a lot of conventions. IEEE came out with a lot of things on 5G. But India side, the toy is coming out, and the wireless planning is also actively working on this 5G, as Sai Dheeraj also said. Sometime back, I was also associated with Ericsson for this 5G standardization. IIT Kharagpur is, there are people working on this standardization, IIT Madras, and many more IITs. Even the government has also pumped a lot of money, 500 crores of money it has pumped on this 5G project, and IIT Madras also developing a test bed for the 5G. So a lot of activities is happening in 5G itself. We didn't miss that 5G bus. So India is actually involved in standardization and contributing a lot for the 5G standards. And 5G is concerned, the frequency is, there are many bands for operating. I just put that 24 to 30 gigahertz is a higher band. And people also plan to work on the sub 6 gigahertz band, especially that, 3 to 6 gigahertz people are planning to use. And the capacity is expected to be 1 Gbps per second. That means the movies and all you can just, fraction of seconds you can just download a movies with the high definition things you can download, and you can just watch all the TV channels. Now with 4G itself, all the TVs, all the smart TVs are using 4G. Directly you are connecting your TVs are using the Wi-Fi data or wired data directly, and they are just we are watching all the TV channels not through the DTH. Earlier, all TVs were using the DTH. That means direct to home technology. That through the VSAT terminals we collect the data, video data, TV channels data from the satellite, and we use it to broadcast using the TV equipment. But once this 5G has come, using the fiber to home technology (FTH), from the FTH, and it supports a huge data bandwidth because of the optical fibers. It is a it is a boon to the people who work. The FTH is a boon to the people who work from the home, because the fiber can support theoretically infinite amount of bandwidth, but practically it is the order of terahertz. That much it can support. So directly I'm getting the terahertz or terabits per second of data to my home, which I'm giving it to my TV, which I'm using it for Wi-Fi to connect mobiles, laptop, etc. So the TVs are directly using that much things, and we are just having all the channels we are watching YouTube, and all the TV channels we are directly watching live. And nowadays the technology has moved from the now no more cinema theaters. People just watch everything on the television itself because of the OTT. Okay, so the technology is growing that much fast, and and the implementation side, there are many things. The NR new radio is the standard for the 5G, like GSM is a standard for the 2G, and for the 4G we call it as a LTE, and for 5G it is called new radio, because the spectrum itself changing. That is why it's a new radio. And another thing is, some of the significant technologies is this millimeter wave communication. It's moving from this conventional band to the higher bands. So therefore, those bands are called millimeter wave. And this we have the NOMA, non-orthogonal multiple access. We were using OFDMA for the 4G. And 5G also, some people initially thought that OFDMA is going to pick up, and it is going to be a hybrid. Whether it is going to be a OFDMA or NOMA, we have to see when the standard comes. But NOMA is picking very high because of the spectral efficiency, which can support. And now, no wonder, the IoT is also going to play a very significant role, and everything is going to get connected with this, internet through the IoT, and the mobile phone is also, we can access everything, anything through with the help of the IoT. Through your mobile phone, you can handle anything or operate anything. So with this applications is video calling, cloud, many more things we are going to see. And this application services, just 1 minute. This application part, this MIMO, let me explain the application part. You can see there are this Wi-Fi and 4G LTE. Let me explain about the, these fundamentals little later. because it requires more time. So let me go through the multiple input, multiple output system. Means there are multiple transmitting antennas, the multiple transmitting antennas and multiple receiving antennas. The advantages of this MIMO technology is it provides a very high data rate. Earlier we were using only one antenna. We have a huge amount of data, but we were using only one antenna to transmit. Therefore, it is like transmitting data very slowly, one after another. Now with the multiple antennas, I can parallelly transmit the data streams. Therefore, the first thing is the data rate is enhanced. And this MIMO also gives a transmit diversity and receive diversity. It's a combination of both transmit and receive diversities. Therefore, the reliability of the communication is also improved. That means the low bit error rate. Bit error rate is defined the number of erroneous bits divided by the total number of bits transmitted. So the number of erroneous bits means the bits I just transmitted a good bits, but it has corrupted by the channel. As a resultant, it become a error. In the detection, I wrongly detect. Okay, that is a error. So the number of erroneous bits divided by the total of bits transmitted. Therefore, the bit error rate parameter always should be low. When you have a low bit error rate parameter, you will get a high quality of service. So that gives the good reliability. On the disadvantage side is the hardware complexity. You need to have the RF chains and the power amplifiers need to fed the lot of power, all that, and the cost is also increasing because of the complexity. But some of the typical applications of this MIMO is this Wi-Fi routers and 4G LTE. Everywhere the MIMO has come, and MIMO is a very well-proven technology and applied in many places. And next is a massive MIMO. That is today earlier people called this as a large MIMO and huge MIMO and massive MIMO, different terminologies. But it's all talks about the large number of antennas which are deployed, either a transmitter, it is deployed both at transmitter as well as at the receiver. And because of that, we are able to get a much spectral efficiency and the power efficient communication because of the transmit diversity. Because of the diversity it provides, the MIMO is provide a huge diversity order, and because of the parallel path, I just reduce the transmit power low. Okay, so that is the power efficiency I can get it from the MIMO, and it gives a more reliability because of the diversity. And large scale MIMO system, the comparison is typical MIMO systems use 8x8 antennas only, or at most 16x. We don't go beyond 8x8 because of the reason is that it is very difficult to do the ML detection at the receiver. So the maximum likelihood detection at the receiver is very challenging using the MIMO. So what is maximum likelihood detection? At the end of the last session today, we are going to practically show you how to do the ML detection and what is ML detection. That will be explained at the third session. But here it is a decoding technique at the receiver. It is very difficult to do the detection for more than 8x8. So therefore people are afraid. But there are certain communication like satellite and other things using the large scale MIMO is very useful. If you see, there is a MST radar center near Tirupati owned by the ISRO. They have this huge dipole like 256 or 512. I visited that place. I think around 256 or 512. I don't remember exactly the number, but that many number of dipole antennas are planted on the ground to know the weather conditions of the different layers of the space, like tropospheric layer, ionospheric layer, different layers of the space they do it. Whenever you launch the satellite onto the sky, it is very essential to know the temperature at a different temperature, the moisture, that means the humidity, at different layers. Different layers will have a different temperature and different humidity level, different gases, everything. To sense all that, we need this, MIMO setup, large scale MIMO setup. And the data rate, whatever the data which collect is also, it can support, tens to hundreds of the bits per second per hertz. That is the advantage of the MIMO, but it is all at the cost of the hardware complexity, no doubt about it. The challenge is deploying the huge number of antenna. It requires a larger space, right? You just imagine 256 cross 256. But there was a dipole means you have to put it on the ground only. There is no other option. now this we can go for this micro patch antenna, which can accommodate within a small size, in a table size or 1 feet size. We can accommodate, or 1 or 2 feet. We can definitely accommodate this micro patch antennas. That is possible, but still the hardware complexity is the main goal. The solution is also we are proposing in one of the sessions, that is a spatial diversity or spatial modulation. Under that, how do we handle the hardware complexity, that we are discussing that. Okay. So the another technology which is another promising technology other than the massive MIMO is one of the promising technology for 5G. Another promising technology what we expect is the cooperative communication. See, this MIMO is well tested and having a lot of solutions. Okay. So before taking this 15 slides, we have completed 14 slides. Let me have any questions from the audience. Let me take now. So far, whatever I thought, if you have any questions, please ask.
Sir,
Yes?
good afternoon, sir.
Yeah.
Sir, in 5G, a single carrier can take how many signals, sir?
Yeah, in 5G, it is like we are not planned any this number of subcarrier things, but
Yeah.
when we plan the orthogonal frequency division multiplexing, at least 128 carriers we can comfortably use it, and people plan to have much more carriers when the wave TMA is employed in 5G.
Okay. Thank you, sir.
But however, this NOMA concept is coming. This NOMA is like one carrier frequency. I'm going to explain the NOMA only with the two mobile users, but it is possible to have a huge number of subscribers also using NOMA. NOMA is alternate to the orthogonal multiplexers. But still, what people are going to use it is we have to wait and see. But we are going to see this NOMA concept today.
Thank you, sir.
Yes, any other questions? Okay, if there are no other questions, let me continue. Okay, fine. See, these people have thought before this 5G came up, this cooperative communication came, and this idea of the cooperative communication is applied in many places. Like it is applied in wireless sensor network, it is applied in IoT, it is applied in smart grids, it is applied in mobile communication, satellite communication, and many sensors. I mean, wireless sensor or wired sensor, many places people start to use the idea of cooperative communication, because it provides a very, good reliability. That is the reason. But what is this cooperative communication? Let me explain to you. See, the MIMO is excellent, but the MIMO is requires a RF chains, multiple RF chains. Like, and MIMO array antennas have to be kept, at a, suppose you are planning a MIMO antenna 8x8 antenna, the separation between the antennas should be greater than lambda by 2, where lambda is a wavelength. So that means this distance between one antenna to another antenna. How do we calculate lambda? Lambda is calculated from the C is equal to F lambda, where C is the velocity of light, is equal to F lambda. F is the carrier frequency and lambda is the wavelength. So suppose we know that this is a carrier frequency, I am going to operate it. So therefore, this velocity of the light is fixed, 3 into 10 to the power of 8 meter per second. Therefore, from there I can calculate the wavelength. So now, after calculating the wavelength, I have to make sure the distance between the two antennas should be greater than lambda by 2. That means that much separation you have to maintain. Why that much separation you have to maintain? And only I can get a spatially separated signals. Otherwise, the two channels will be correlated. So this is an essential condition in the MIMO. So therefore, the signal should be statistically independent. That is the condition of the MIMO. For achieving that, you need a space, right? In the mobile phones, you cannot allocate that much space because the mobile phones are handheld devices. I want to keep it only with the hand. I cannot keep, mobile phone, somebody carrying a mobile phone for me. That is not possible. So therefore, implementing this MIMO onto the mobile unit is very challenging because of the hardware complexity. Because the mobile uses battery operated devices. So these, if you use a multiple RF chain in the MIMO, it is no longer possible because the battery will drain quickly. We cannot communicate. We cannot keep on charging the mobile phone. Therefore, because of that, achieving mobile MIMO onto this mobile unit is very challenging. But I want the data rate. But I want the reliability of the MIMO. I want the data rate. I want this, efficient, spectral efficiency of the MIMO. So therefore, people implemented the MIMO with a trick that is called distributed spatial diversity, or in short, distributed MIMO. That is what I written it as a distributed spatial diversity or distributed MIMO, where the single antenna mobile units which are distributed in different geographical locations. That means mobile phones are distributed in different geographical locations, right? Which can generate a multiple communication path. But for that, it has to collaborate with each other. Or for that, it has to cooperate with each other. So the practical implementation of this distributed spatial diversity requires some sort of cooperation among the mobile units. That means some protocols we have to write so that these mobile phones will cooperate with each other. So the protocol we need to design and then implement, then only this cooperation is possible. So therefore, there is a lot of scope both in physical as well as in data link layers. In cooperative diversity, the mobile units share their antennas with other mobile units and forms a virtual antenna array. It is not like the mobile units are geographically located at different places, they are isolated. They can form a virtual antenna array with the help of this cooperating protocols. Okay. Typically, a cooperative diversity system will have a source terminal, a relay terminal, and a destination terminal. Like this, I'll just explain with the help of this diagram. A cooperative communication can have a source and a relay and a destination. So the source and relays, they cooperate with the destination. How this is done is with the help of the two protocols. One is called amplify forward, another one is called decode and forward. So the relays, whether it is analog data or digital data. If it is analog data, then we need to amplify and forward it to the destination. The relay will amplify the signal and forward it to the destination. Otherwise, the relay will decode the data. If it is a digital data, it will detect or decode the data and forward it to the destination. It all depends upon what is the kind of modulation or what is the kind of waveform you are transferring. Now, I considered a system where I am planning to use digital modulation. For example, I written a MPSK constellation. MPSK is the order of the modulation. If I put M is equal to 4, then I will get a QPSK. QPSK is a very standard modulation scheme for the CDMA systems. And in the Wi-Fi routers, we go for the 8PSK. Another variant of this is the 8PSK, where we just use eight symbols. In QPSK, we use 4 symbols or 4 waveforms, we can see. Now, from the source, I just transmit the S. S is this QPSK modulated symbol. That means one of the waveform I transmit. There are 4 different waveforms in QPSK. One of the waveform I'll just transmit it. The receiver, I need to detect which waveform was transmitted. Okay, I have the information bits. I just modulate using the QPSK modulation at the transmitter. So in the QPSK modulation, the information bits, those information bits, I just use to modulate, this carrier user technology called QPSK modulated. So the one of the carrier is carrying this information. One of the waveform is carrying the information. So out of the 4 waveform, one waveform carries that information to the destination. At the destination, I know that it is going to be one of the 4 waveforms, but which waveform it was transmitted, that I need to detect it. For that, I use the maximum likelihood detection at the receiver. Sometimes, if the channel between the source and destination is weak, then we need to go for this relay-based communication. The relay does not have any data to transmit, even though the relay is another mobile phone, but at that point of time, it does not have any data to transmit. That is why we call it as a relay. The word relay has come from the relay game. I think many people would have seen the relay game. That means somebody will carry the ring. It's a kind of ring kind or something carry some object in the hand, the first runner will be keep running. He will not run for the entire circle. He will run for half of the circle and hand over the relay to the another person. Another person will carry this data and reaches the destination. That is called relay game. So based on that, this relay has come. The relay will carry the source data and reach it to the destination. That is why it is called relay. Now I'll explain this diagram. There are two time slots, two orthogonal time slots. Orthogonal time slot means there is no overlapping between the one time slot to another time slot. That is why we call it as a orthogonal time slot. So there are two time slot 1 and time slot 2. The time slot 1, I'll just transmit one QPSK symbol, one QPSK waveform yes. And when you transmit the waveform at the transmitter, the waveform is very pure. But what happened when you put it onto the wireless channel, because of the multipath propagation, which changes the parameters of this waveform. That means changes the amplitude, it changes the phase, it changes the drifts of frequency, everything it does. So those changes, I just call it as a, I just call it as a H. H is the channel impulse response. So the channel impulse response is specifically for the wireless channel. The wireless channel, because of the multipath propagation, what kind of effect is happening to my signal is given by this H. The H is between the source and destination, therefore the suffix was ST, HST. And the noise is because of the thermal noise. The moment you switch on the equipment, the thermal noise is going to come, and the thermal noise is definitely it is going to be there. But the one advantage of the thermal noise is the average noise variance. That means the noise power is average, and therefore it is easy to handle the thermal noise, which we modeled it as a additive white Gaussian noise. So this N represents the thermal noise, which is modeled as a additive white Gaussian noise. Fine. Now this pure S and now change it to R. Now it was like you just take your your photo, your child, when the child is born, it was like yes, the pure nothing knows about this world. Okay, but now after living 40-50 years, now it is become R. That means corrupted by the channel gains H and the additive white Gaussian noise N. Now the challenge is for the God is to invent whether what we sent is this baby or now this corrupted baby. You have to try to recover.
Hello.
Yes.
Sir, can I ask one question here?
Yeah, definitely.
Sir, you just said after 42 year got corrected. Sir, can you please repeat, sir? I have missed that
No.
words.
No, it was fun. I was just
Okay.
telling.
Okay.
Just it is the symbol or the waveform which was transmitted at the source was without noise.
Okay.
Whereas at the receiver, I am not receiving S, I am receiving R. So
Okay.
the
Okay.
challenge of the receiver is to detect what was transmitted.
Okay. Okay, sir. Okay.
Okay, that is what I am just making as a just funny way. I was telling that was a child when it was born, it was very pure, right?
Yes.
Without
Yes.
knowing any, it is uncorrupted mind.
Yes, sir. Yes, sir.
After living so many years, when the child is growing year after year, the
Yes.
mind
Yes.
is also getting corrupted.
Yes.
And when
Yes.
it reaches 40-50 years, it is fully corrupted mind. Okay, so that was a fun thing. I was just telling the
Okay.
God will be looking at the child and see this. I sent a very pure one. Now you are just so much corrupted mind. Okay,
Okay. Okay, sir. Thank you, sir.
okay,
Thank you.
that is what. Now I just transmit this information. I broadcast this information onto the air. So the receiver destination was picking up the information, and the relays was also picking up the information simultaneously. Therefore, the time slot one, both the destination as well as relays were receiving that information. Now the destination received one copy directly from the source, and the relay now it is detecting or it is like decoding that source information, and then it is retransmitting that information. It is like, whenever the Prime Minister comes, there is a translator also. Or whenever a VIP comes from the North India to Tamil Nadu or Chennai, there is a translator also comes. So the VIP will be speaking in his own language. Suppose some VIP come from a country, say Spanish or Spain is coming, and he talks in Spanish, and there is a translator also associated. He translates that to the local language, right? But it is always a challenging. Sometimes what the translator does, we do not know. He may translate it correctly or he may translate it wrongly also. We do not know. But we just receive that. One is we just receive directly from the original Spanish man what he's talking, and also we receive that copy from the translator. Like two copies we receive. So this relay decodes that information either correctly or wrongly, we do not know. Therefore, I just put it as a SCAP. SCAP is the decoded information of the source data. And that is that it is forwards in another time slot, orthogonal time slot 2 to the destination. Now the destination receives two copies of the same information. So suppose some information you are just listening one time, but now the same information you are listening two times. So I can just make a good decision because the two copies of the same signal is available. I can use any of the conventional diversity combining technique and get a better reliability. Therefore, this cooperative communication enhances the reliability using the distributed spatial diversity or distributed MIMO concept. And this is going to be one of the key technologies for the 5G. And another key technology is the non-orthogonal multiple access. So the 4G I already told OFDMA it is adapted very successful, fine, and 5G is expected to adapt NUMA. And this OMA orthogonal multiple access is concerned, each user can exploit the communication simultaneously. Simultaneously means same time, same frequency, same code. To avoid the with multiple interference. See, one thing is general. Simultaneously, when you transmit two information on the same frequency band, it leads to the interference. Like simultaneously, you transmit two information on the same frequency band. There are two antennas. For example, you QPSK antenna use the same frequency above and below. But if it without any coding technique, if you directly transmit, it leads to the interference. Okay, that is what we studied in the FM, right? In the fundamentals of the FM, we studied when you have the two transmitting antenna, one receiving antenna. If you take two symbols simultaneously without any coding, if you transmit it, leads to interference. So we have to transmit it with a different time delay, and only it is possible to avoid the interference. But with the orthogonality concept, that means if you use the orthogonal codes, that means only the intended user will receive the required signal, other user will just neglect it. If it doesn't have the code, he cannot decode that. So therefore, the coded information you can transmit, that is the orthogonal multiple access. But the interference will be there, but still you can control the interference, whether it is a CDMA or OFDM. Especially in CDMA, power control is a very key parameter. You have to use the power control algorithms, and only you can avoid the interference. Otherwise, interference is a significant matter. But in NOMA, again, the interference is going to be there, but we are going to attain the spectral efficiency because here one carrier frequency, multiple users can simultaneously use it. How do we achieve is through different techniques. One is called power domain NOMA, another one is called code domain NOMA. So let me explain this with the help of this diagram, the power domain NOMA. So like I just transmit the same signal. There are two users. One is the one user is at the far user at the cells. This is a hexagonal cell. This is a mobile cell. Sorry, the mobile communication cellular structure. And this is a hexagonal structure. That is why we have this cell phone. We call it as a cell phone, right? Because of this cellular structure. So this hexagonal cellular structure, generally the base stations can be placed at the center. Here I just place it at the one end because of the geographical conditions. Say there because of the mountain, other things, we can place a base station. So it is up to the system designer where where to place a base station. Now I placed a base station one way because of the to explain this schematic diagram. There are two users. One is the near user, another one is called far user. The far user is distance wise is very far from the base station. Near user is very close to the base station. And since the near user is close to the base station, the channel is expected to be strong, right? That means when you can transmit with low power. That means the base station can transmit a waveform with a low power to the near users. You don't have to spend too much power because the channel, because of the proximity, the channels are strong. That means the channels is having a good CSI. And the far user, definitely, very clearly, it will have a weak channel because of the distance. The path loss is path loss is inversely proportional to the distance. So the distance increases, the path loss is increase. Is going to increase. That is the main thing. Fine. Now we come to this point. There are two users, near and far users, but here we are going to use only one carrier frequency. That is the thing. I am going to use a superposition coding at the transmitter side. The transmitter side, I am going to use a superposition coding. There, I am going to combine the two signals. One signal, that is M1 of t for the user 1, near user, or M2 of t is for the far user. That means two different messages I am going to combine, make it as a one composite signal. The composite signal is going to have combination of two different messages, but the carrier frequency is same. That means one single carrier frequency and just transmitting two messages. Therefore, the spectral efficiency increases. I am efficiently using the spectrum. That means one carrier frequency, two simultaneous users, and simultaneously. That means time is also same. So same time, same carrier frequency, two users can use it. But how do we decode? How do we handle the interference? Is with the help of the channel, the multipath propagation, different channel. Because the two users are spatially different locations and the channel gains are going to be different. With the help of the different channel gains, I can decode the data. And another thing, what I do in the superposition coding is I just transmit high power for the far user and low power for the near users. Okay, because the near user has a strong channel, therefore I'm going to use a two power coefficients. One is called alpha 1, alpha 2. Alpha 1 is for the far user, alpha 2 is for the near user. For alpha 1, I'm going to allocate more power. Alpha 2, I'm going to allocate less power. But the total transmit power is fixed. Therefore, the sum alpha 1 plus alpha 2 is equal to 1. Since because of this, for example, if I have a, say the power is say 300 milliwatts or something, I'm just transmitting, or 1 watt I'm transmitting, out of the 1 watt, 75% of the power is given for the weak channel for user, and 25% of the power is allocated for the near user who has a strong channel. That is the idea of the power domain NUMA. That is why it is called power domain NUMA. But the far user is comfortably can decode because of the the power allocated for him is more. But in the case of near user, it is not possible because the power allocated to the near user is only 25% of the power. So first, since same carrier frequency, first you will listen only the far user signal. Okay, first you will detect the far user signal and subtract it from the received signal. So I just receive the signal. First, I'll detect the far user's data and subtract the data from the received signal. Then I'll get the new received signal. That means from the subtracted data, I try to decode my own signal. That is a near user's signal. So this technique is called successive interference cancellation. That is called SI. In short, we call it as a SIC. So with the help of the SIC, the near users decode its own data. Okay. And there are many variants. This NUMA is now a very hot topic for the researchers who work in this wireless, 5G wireless. And there are many variants of this, variants of this NOMA is available, like multiple users NOMA is available, different modulation technique, code domain, power domain NOMA. When you use the cooperative idea onto the NOMA, how to use. So there are much more, research problems are available in NOMA. The people who are interested to work to do research in this area definitely can choose NOMA. You can definitely get a good number of research problems using NOMA. Next, the millimeter wave communication. So this is, as I explained many times, the millimeter. So let me stop here. Any doubts? Any questions?
Sir, excuse me, sir.
Yes.
Hello.
So according to successive interference cancellation,
Mm.
the strong user signal won't be first decoded, next the weak user signal decoded, like that I studied, sir.
Yes, correct. Yes, your understanding is correct.
Okay, sir, but you told now weak user signal first we will decode, next we are...
No. If in the sorry, if I hold it in that way, that is not way. In the near user, when the signal reaches, when the near user receives the signal, first it will detect, the far user signal.
They Anna principal gold stamp principal stamp.
No.
Stamp pad.
See, who is please the listeners, participants, please turn off your mic. Yeah. So in the near user, what do we do is, how do we detect or decode the signal is, first we'll decode the for user signal. Why we decode the for user signal? Because for user we pumped more energy, like 75% of the power is pumped to the for user. Therefore, first we decode the for user data, and then we subtract the for user's data from the received signal. Then from the resultant signal, I'll decode the near user's data. This is called successive interference cancellation. Okay. Clear?
Yes, sir, thank you, sir.
Okay.
Hello.
Good. Yes.
Namaste, sir.
Yes.
So, sir, I want to know that whether millimeter waves are coming into picture in 5G or 6G.
Millimeter wave is going to be in 5G. The next slide is going to be about that. The millimeter wave is going to be 5G, because 5G we are able to get more bands because of this, millimeter wave only.
Okay. And in that millimeter wave range, if we consider the transmission of power and compare with the previous frequency bands, so whether millimeter range will going to be more effective or what? Can you please highlight on that?
No, main thing is, see, the millimeter wave thing is, when you go for higher frequency, we are going to explain all your questions. Okay, your question
sir.
is, in this coming slide, your question is, whether can we go for higher power? See, generally you know very well. I think all the people who studied physics, they know very well that whenever we go for higher and higher frequencies,
Yes.
okay, we try to limit the power. We will not pump more power.
Yes.
When you pump more power onto the high frequency, it is hazardous.
Okay.
Because higher frequencies naturally attenuates more. You know very well, the path loss is inversely proportional to the frequency. When the frequency increases, the inversely proportional to the lambda. When the lambda, the decreases, the path loss is going to be more. So it is going to be more path loss when we go for higher frequency, especially the 60 gigahertz is unlicensed bands. What the reason is the path loss.
Okay.
Therefore, it is more suitable for the indoor environment only. That is what I am going to explain in the next slide. Indoor environment only.
Okay.
But the challenge is, we cannot pump more power. The power has to be limited. See, for example, X-rays we pump more power, right? But it penetrates a human body and shows only the bones. But if you take 10,000 X-rays in a year, the people are more likely to get a cancer.
Yes, sir.
So therefore, with that inventions, people generally do not wish to pump more power onto the higher frequencies. But we still, these higher bands, there are many other benefits. One is we get a huge bandwidth and data rates are, because of the huge bandwidth, the data rates are going to be huge. And because we can transmit it at a faster rates, all that we can enjoy, but at the indoor environment, okay, where we transmit limited power.
Okay. Thank you,
Okay,
sir.
okay, fine. So anyway, the millimeter wave communication, the motivation is we were operating still sub 6 gigahertz only so far. But the main motivation is the bandwidth is not sufficient for us in the 4G. Because why the bandwidth is not sufficient? I am having lot of applications on the internet. I want to transmit high definition video, uploading, downloading, and interactive video, high definition interactive video. Somebody in the US, where we want to have a very rich video quality interactive video, we want to transmit it. All that demands huge bandwidth. So huge bandwidth, is possible not with the current 4G standards doesn't allow that. Therefore, we want to move to the higher bands. So, but in the millimeter wave, in the 5G, we want to use the entire millimeter range is 330 gigahertz to 300 gigahertz. But still, we call this 30 gigahertz to 300 gigahertz. That is the millimeter wave band. But we are in the 5G, we are going to explore between 24 gigahertz to 29.5 gigahertz. This is around 28 gigahertz only we are just want to explore in the 5G. Along with that, we are having go to have a lower and mid bands. That means 3 gigahertz to 6 gigahertz. That band is also we are planning to operate for 5G. So that is the mid band is 3 to 6 gigahertz. The higher band is 24 to 29.5. And there is some people were talking about the 60 gigahertz. There are a lot of many papers on this terahertz and 60 gigahertz communication. But the challenge with the 60 gigahertz communication is heavy attenuation. Attenuation is more in 60 gigahertz, and you cannot have it in outdoor because of the rain and other things. This waves will die. You get distracted a lot. Therefore, it is more suitable for the indoor communications. And this one of the motivation for this millimeter wave is Ericsson and did a research in the North America. The mobile phone users is on an average use 7.4 GB data per smartphone per month. 1 month people were just use 7.2 GB. It was taken long back, but it is going to be expected to be double in the year, or it is going to be expected to be almost sevenfold. I think, sorry, not double, sevenfold in the year 2023. Just think now we must be around sixfold. So that means, in by the year, this year 2021, we may be around be operating 35 gigabit GB data per month, or maybe more than that. That much, because we are using smart TV, right? We are using smart TV and we are using internet continuously, and so therefore we need a huge data. But still, the smart TVs are not mobile phone. From the it is not like we are operating that bands. We are using the FTH. Tomorrow we may use using mobile itself. All this these things from the mobile itself. I can project this the TV channels. I just from the mobile you can see you are watching a lot of ads also. From the mobile itself you can stream the video channels or the TV channels, everything. There is a need for the new spectrum, and this millimeter wave communication helps this 5G to find those bands. But the challenge is, this attenuation and other characteristics. But advantage side is it provides a larger bandwidth, the 2 gigahertz bandwidth. And when the larger bandwidth is available, you can support a large data rate and also large number of subscribers. There is another advantage is whenever the increases that antenna size, the antenna is proportional to the wavelength, right? So when the frequency increases, wavelength decreases, and the wavelength decreases, the antenna size also decreases, right? That is the basic physics. So when the antenna sizes decreases, I can comfortably bring the antenna inside this portable devices. Okay, these are all the advantage of going to the higher bandwidth. But there are disadvantages. One is this: how to handle this RF signals, the huge RF amplification of the RF signals, and the signal conditioning, signal processing of the RF signals is a huge task. And lot more research is going on the RF side, how to handle this hardware. Another limitation with respect to this, when you go for higher bands like 60 gigahertz typically, they are supports only the line of sight propagation. Like example is very high, like terahertz. This infrared LED is a terahertz, more than terahertz. Okay, those things depends only line of sight. In the infrared LED which we use in the TV remote control, it's only line of sight. If you put any obstacle, your remote control will not work because of the huge frequency and very low wavelength. So when we go for higher and higher spectrum, it expects a line of sight. But generally, indoor communication, line of sight chances are less because you put the Wi-Fi tower in one room and you will work in another room. The chances of LOS is less. But still, we manage all that. Those are all the challenges with respect to the millimeter wave communication. And the outdoor environment, if not a free space optics, free space, we have this foliage. That means the trees between the buildings. It absorbs the electromagnetic signals. It eats up the electromagnetic signals. We will not get the signal on the other end. Those things are more. Therefore, we significantly use, or we mostly use these higher frequencies at indoor, and the conventional sub-gigahertz bands in the outdoor. So this is about using the millimeter wave communication. Is one of the key technology in 5G. Another key technology is the spatial modulation. I talked enough about this hardware complexity, which has created the MIMO. Look at the conventional MIMO setup. MIMO channel, I just first diagram, the conventional multi RF MIMO. You can see in this multiple antennas, and you can see the RF switch, and you can see the RF chain. RF chain means it will have this model like AF, audio frequencies, then intermediate frequencies, then RF. Inside the RF chain, everything will be there along with this baseband. So we get the data input, which is in the very low baseband frequencies or AF frequencies. And then I do first set of baseband processing. I'll do amplification, I'll do signal conditioning, modulation, channel coding, and cryptography. That all the blocks will be inside the baseband. After that, I'll just upconvert the baseband into the RF chain. So I'll upconvert it into IF frequency, then I'll do the amplification, signal conditioning at the IF range, intermediate. Then I will again upconvert it into the RF required RF chain. Again in RF, we do amplification and signal conditioning. But this requirement of the RF chain is a huge, requires RF amplification, requires a huge power. Therefore, there is a need. All these things are possible only in fixed wireless services. When it comes to the mobility, the battery doesn't support all that. So we need to have a single RF chain. That single RF chain technology is called the spatial modulation. So the spatial modulation, we are going to have a independent separate sessions. Two sessions on spatial. One is on cooperative, another one is on spatial modulation. We are going to read this about the single RF chain under the spatial modulation. Okay, but what is the problem, sir? What is the problem with the conventional MIMO? You may have this question. I'll just explain you why this spatial modulation is required. What is spatial modulation? How do we implement? We are going to see in the fourth day and fifth day in 5G. The motivation alone I am just going to give now. Look at the V blast. The vertical bell apparatus layered space-time coding is called V blast. There are two symbols, S1 and S2. Those symbols are fed to the antennas S1 and S2. Okay, and it is transmitted same frequency, simultaneous transmission, and two antennas S1 and S2. Why we call it as a spatial multiplexing? Because both the antennas use same carrier frequency, same time. but from different geographical locations. So that is why it is called spatial multiplexing. You know very well about the frequency division multiplexing. That means two different frequencies I just combined. That is called frequency multiplexing. Time division multiplexing, two different time slots we multiplex. That is called time division multiplexing. Now, because of the two different spacing, same carrier frequency, same time, but two different geographical locations. That is why it is called spatial multiplexing. So we enjoy, it is also spectral efficiency. We enjoy the spectral efficiency and simultaneous transmissions. So therefore it is good. But look at the two antennas are essential. That means two RF chains are essential. Without that we cannot do. Okay, sir. Next, better scheme than the V blast is the orthogonal. Orthogonal STPC. That means space-time block ports. And this space-time block ports is like the two. There are two symbols S1, S2, but the same symbols are repeat with a different time slot. S1 was transmitted from the first antenna. S2 was transmitted from the second antenna in time slot 1. But S1, S2 uses the same. This first antenna, second antenna uses the same carrier frequency. But S1 is transmitted from the first antenna in time slot 1. S2 is transmitted the same time slot 1. S1, S2 in the same time slot. Now, I'm just repeating the same symbols, but from the different antenna. It will give the transmit diversity. That means I'm repeating the S2 from this antenna 1. That means this antenna location is spatially different. And the S1 is repeated from the antenna 2 from the different time slot. So I'm exploring the both spatial diversity and time diversity. Therefore, it is a space-time block port. I am getting both space, time diversity simultaneously, and therefore it increases the reliability of communication, increases spatial diversity, that means spectrum efficiency, and gives a much better. So here, so what we are going to do now is this V blast structure. Mic is on. Yes, fine. So let me continue. What is that, the conventional, what is that new it is going to bring in the spatial modulation? Conventional V blast structures already in the market. Everybody using those devices. And orthogonal STPC also on the market, and people started to use it. And it is very popular. Orthogonal and quasi-orthogonal space-time block ports are very popular. I think from 2000, I started my research in 2005. So in 2005, we started my PhD program. But it was like 2000 onwards, there is a very excellent book by Peter Stracko on this space-time coding. Those days, it was very, very popular. So 15 years back, it was very popular. And this orthogonal space-time block ports is fine. What is that? We are trying to give something new. This is spatial modulation. We can effectively reduce the number of RF chains. Why we need to effectively reduce the number of RF chains? One is hardware complexity. That's fine. We are going to reduce the hardware complexity. Another thing is the inter-channel interference. Whenever we have these two antennas, even though they are spatially separated, they are using the same carrier frequency. There is a chance of interference. That is called inter-channel interference. So that we can reduce if you use only one RF chain at a time. Okay. And in the V blast structure, we need to have these two symbols simultaneously. We need to transmit. For that, the two antennas have to be synchronized, right? So the inter-antenna synchronization is also a challenge. So that we can, mitigate. Therefore, at the receiver, if the inter-antenna synchronization is not there, the decoding is difficult at the receiver. So that we can avoid it, if you use the spatial modulation. And the multiple RF chain complexity, circuit mismatch, coupling, all these things are challenging. And the overall energy you can reduce if you select only one RF chain. So therefore, in essence, in the spatial modulation, I am going to use, okay, I am going to select one or limited number of RF chains, or I am going to use one or two RF chains for the multiple transmitting antenna. Okay, so therefore the antenna itself is going to, there are two variants of the spatial modulation. One is called space shift keying, another one is called spatial modulation. In the space shift keying, it is like we have two bits. One bit is called logic 0, another one is called logic 1, right? Whatever I speak using the ADCs, you are going to convert it into the analog data into the digital data, right? So the digital data is going to be the form of zeros and ones. So the information bits is also is always going to be 0 and 1. So instead of transmitting the information bit, I am going to just transmit two things. For example, I'll just in a way for the explanation sake, I'll tell you. For example, logic 1 is red color, logic 0 is green color. So whenever logic light, whenever I see the red light, I'll assume I understand. So no transmission, no receiver complexity, no way to do the channel decoding. This nothing. I just see the red light. I write it. Yeah, the transmitter signal was logic 1. I just see the green light, logic 0. So that means this is called space shift keying. Whenever in the RF antenna, I'm just transmitting a waveform, and the receiver don't have to decode and find it out what was transmitted. If it is transmitted from this antenna, that is sufficient. It has to identify only which from which antenna it was transmitted. That identification is through the channel gains, and nothing else. It is just going to identify which antenna was transmitting or which antenna was eliminated. That I identify from the channel gains. And from there is no complexity, no decoding, nothing. I'm happily just reinventing and detecting what was transmitted. So it was logic 0, logic 1. So substantial improvement in reliability. That means the quality of service is going to increase definitely because of the low bit rate, because of this index modulation. Index modulation is also similar to this SSK. In addition to that, in order to increase the data rate, I am just including the modulation also. So the combination of a modulation and antenna index is going to give the spatial modulation. I am going to do the modulation plus this spatial keying. So with this new idea, new technology, I am going to reduce the number of RF chains. Therefore, I am just reducing the hardware complexity, both the transmitter as well as receiver. So it is a very excellent idea to have the limited complexity. Therefore, the idea of MIMO can be implemented onto the mobile units with the help of the spatial modulation. That is the advantage of the spatial modulation. So the final slide about that is the Internet of Things application side. Internet of Things, and you know very well, Internet of Things is there are 4 important features. One is the user data. How do we collect the user data? User data are collected with the help of the sensors. For example, I just Food Corporation of India has a large number of godowns all over the India to store the food grains, right? All the wheat, paddy, everything it will store inside this Food Corporation of India godowns. Now I need to sense the temperatures. What is the temperature? Because it is all food grains. You need to take care. There should not be any temperature, any fire or other things. So the temperature is, you need to know the temperature. And I need to know the moisture. It should be dry. Otherwise, if it is wet, then there is a problem. I need to know the moisture level. So the temperature, moisture level, I can just, calculate by keeping, or I can sense it by keeping the temperature and moisture sensors. And I collect the data from there and transmit it to my cluster head in the wireless sensor networks or IoT framework. So the cluster head send this data to the IoT gateway. From the IoT gateway, it will go to the cloud. So the entire India's, all the food corporation, the entire in our country, we have the FCI, Food Corporation of India, several places. Everything data is available at one place, in the cloud. So I can store all the data in the cloud. The next process is I'm going to analyze the data. That is called big data analysis. The big data analysis is done with the help of the machine learning, deep learning, or artificial intelligence algorithms. And this big data analysis, I'll just find it out, what kind of moisture levels are available, how old the grains, food grains, and what are the things I have to do. Everything I'll just calculate at one place. And I'm going to send this information to some central server. You just the wheat, this wheat at Punjab is 30 days old, and the wheat at stored in Punjab is 30 days old, and the wheat which is stored in some other part of the country is say 128 days old, 240 days old. So all the data I'll get, and here the moisture is very high, so therefore we need to see some place, some part of the country, the rain is going to, it is a rainy, therefore the moisture level is less, therefore please consume this food grains as quick as possible. So it will be transported to other place and it will be consumed there and the food. So it is like, we need to have this analysis is essential for this country. Therefore the internet of things plays a very significant role, and we are going to this IO, the 5G is going to support the Internet of Things in a very big way. And now people have come out with Internet of everything, IoE. So Internet of Things has plenty of applications in the agriculture area, in the smart homes, all the home appliances are connected to the IoT gateway, and therefore I can here I can sit and see what is happening at my home, and I can just watch, turn on 10 of the TV, and I can watch the TV from here. I can turn on the refrigerator, turn off, and everything I can do smartphone. The factories automation is possible, and the factory owner may be at one place or supervisor may be another place, and they can remotely operate their machineries. And the healthcare domain, the artificial intelligence is going to play very big data. I think government very recently launched the digital health records to all the citizens of this country. And once the digital health record is available, it is going to tell you if you are a diabetic. It will tell you, see, I have seen your banking information. You are purchasing the food from the from say some pizza centers regularly, and you are a diabetic. Please do not purchase. It will not allow you to buy order for any food items related to the sugar, which has a lot of sugar content. So that much healthcare it is going to happen because of the artificial intelligence. So like it is going to be a doctor is always going to be with you, so, or a health trainer or healthcare person is going to be with you and is going to suggest you what to do. And in this pandemic situation, you know very well the healthcare systems play a very significant role, and this application of this ML algorithm on the or IoT or application of this AI ML deep learning algorithms on the healthcare is going to be a big cluster area. And this 5G is going to support IoT in a big way, because you need to transmit data right to the IoT gateway. Without data, you cannot do anything. So this data transportation is possible because of this 5G. And everywhere they collect the data nowadays. And smart grid, all the power grids nowadays, the conventional power grids are becoming smart grid, and the energy transfer and the power line communication, a lot of things are happening in that area, and IoT is playing a significant role. And the smart cities, the street lights are going to be automated. The water is going to be, where when water is going to be available. All the information about the city is going to be operated in a smarter way. So IoT has got plenty of application. Here I listed a little bit, and the 5G connected with IoT is going to be the future. And there are a lot of potential research problems is available, especially from the sensor node to the IoT gateway. That is a 5G place. Okay, and the selection of the cluster head and lifetime of the wireless sensor nodes. The nodes which are going to deploy the wireless sensor node, which collects user information or climatic condition, everything it has to collect, right? So the data's the lifetime is also limited. Which one we need to identify as a cluster head? How to transfer the data from the cluster head to the IoT gateway, all these things are, are to the cloud, lot of scope is all there. And what kind of processing you are going to do? Where do you do the computing? Whether it is at the fog level, fog computing, or it is going to be the cloud computing or edge computing. So all that is the question. Whether it is a time sensitive application, you cannot do the computing at the cloud because it is a very time sensitive application. So therefore, the fog computing you need to do, or you need to go for edge computing. Depends upon the applications. Okay. So all that we need to look at it IoT application perspective. Okay. Now what do I do is the fundamentals of the mobile communication. We need to have. We are going to have it in the afternoon session. Afternoon session will start with the fundamentals of the mobile communication. Then we will go to the next sessions, the programming part. The programming part, how to implement that, it will be taken by Mr. Kripagaran. The fundamentals of mobile communication I will cover. He will also cover some questions in the afternoon. So I'll stop here, and if you have any questions, I will take up. So feel free to ask the questions.
Good morning, sir.
Yes.
Sir, regarding this STBC code in MIMO communication,
Yes.
sir, in the first time slot, we are sending S1 symbol, then S2,
Yes.
then S2 conjugate, and in the next this one.
Yes.
Sir, what the significance of sending this conjugate? I understand to make it orthogonal, but why it is negative sign is that?
No, that
Negative
is a
S2.
reverse of this waveform, no?
So why it is required? We can directly send S2.
No. You have to send a reverse, and you have to delay it. For that only that is coming. So the waveform, you are just going to reverse the waveform and delay it by a tau period. That is how this minus, and if you do that, calculations, it will come. If you do the derivation, it will come. Minus sign and then conjugate will come.
Okay.
It
And
is a part of the
thing,
derivation. It's a straightforward one.
okay,
Yeah.
sir. But same thing is not applied to S1 star. Do
That
not
is what
use
it is a part of that derivation. If you see the derivation, I didn't bring the derivation part
Okay, sir.
of this orthogonal STBC, but it is a part of the derivation. The minus sign will come automatically
Oh, okay.
in the derivation itself. So that means the waveform will get reversed. Okay, whatever you are transmitting, the waveform will get reversed and delayed.
So now,
That is how we will get the orthogonal.
okay, sir. Thank you. Hello, sir.
Yes.
Inter-channel interference.
Yes.
That is caused in here it is said coupling of multiple symbols in space, which increases signal complexity, signal processing complexity. So here there is possibility of losing data. Okay, so how we can cope up with this situation?
No, yeah, inter-channel interference, what will happen? We will be able to recover the data with a lot of noise, with a lot of interference.
Yes, yes.
Okay, we will not completely lose the data because of the techniques which are involved. But the interference significantly reduces the interference to signal to interference noise ratio.
Yeah, but in this case, there may be maximum chances
But
of
only
losing the data.
no, the processing at the delay is more complex.
Okay,
What
okay.
we get is a signal to interference noise ratio, but we need to recover the signal. The conventional techniques are available how to recover the signal, but only the thing is complexity is more.
Okay, okay. But in that case, sir, whether we can retrieve 100% data, is it possible?
Yeah. See, it is like how you detect things.
Okay,
Okay, whether how do we detect the things is always a challenge.
okay, okay, sir. Thank you, sir.
Hello.
Yes.
Good afternoon, sir.
Yes.
Sir, my doubt is regarding resource allocation in 5G,
Okay.
sir. So, can you elaborate, sir? Because I have been teaching this subject, mobile communication, but I just started reading 5G. And recently I have taken admission. So my area is going to be 6G, resource allocation in 6G. So, sir, can you guide me how should I proceed from 5G to 6G? And
Okay.
whether the resources in 5G are they going to remain same in 6G, because the operating frequency is in terahertz. So, how much it will be feasible, sir? And if I want to introduce AI in that, so, sir, I need a little
Yeah.
bit clearance on this topic, sir.
Okay. Okay. There are three questions. First is about this resource allocation. Then we'll go on. The resource allocation is a see, actually in communication there are different layers. One is called a physical layer, another one is called data link layer. Then we have a network layer. Then we have the transport session, application, all these layers. But generally, the faculty members from the EC background, they work on physical layer and data link layer. And the faculty members from the computer science background, they work on, EC also people work from the physical layer, data link layer, and network layer. But only limited people works on the network layer. Computer science, again, they work on all the higher layers, network layer, data link layer. They may not work in the physical layer because the backgrounds are different. Okay, you have a different background knowledge to attain this. Whereas this data link layer problem is a common to both computer science as well as EC. Most of the people who work in data link and network, it is a common area, a networking protocol, both of us work. So this resource allocation falls on the data link layer. And how do we see when the resources is available? To whom do you allocate? What is the way to allocate? So that is always there. So conventionally, there are technique multiplexing and multiple access techniques. Multiplexing is different from multiple access. So one carrier frequency, how do multiple users use it? Whether it is a TDMA technique or FDMA, WaveDMA, or CDMA, or the non-orthogonal way, all that is the resource allocation cases. And how do we allocate the channels to the users is the resource allocation, typically data link. Always there is a scope to find something better than the existing in the case of resource allocation. Okay, though there are many resource allocations available, techniques are available classically in 4G, LTE, 3G, PP standards, but still there is always scope. You can take up the problem related to the resource allocation and the data link area. Fine. That is the first question. And second question is about the 6G. 6G is concerned, see 5G, we are operating, even though people in the textbooks and in the magazines, everybody starting saying different bands. I just closely watching. I think this 28 gigahertz band and 40 gigahertz band, I think these are all going to be there. Especially this 28, more chances are there. Even though people say 28, 40, as well as this 60, the three bands they are telling in 5G. But somehow people don't nowadays talk about 40. People, this Samir and all, they purchase a lot of things in a very large bandwidth things to handle any 5G or 60 things. But this 5G is concerned, mostly it is going to be on 28 gigahertz. So all the resource allocation problem will be around 28 gigahertz. And with respect to the 60, it is going to be terahertz. So therefore, completely, lot of change in the technique, both in physical layer and data link layer is going to happen. You can take up this idea, and already terahertz communication, even the projects are already on. I also submitted a project in the core research grant for this on the terahertz communications. Yeah, people are already working terahertz. It's going to come definitely. You can work on 60. It is going to come. And primitively, the third question is AI or ML can I apply on 60? But right now, as a researcher, if you are a PhD student, do not go in that way because it's a new technology. Initially, you will not get any literature application of the ML or AI algorithm for 60. You will find it difficult. So my suggestion is first you just try the conventional solutions, theoretical solutions for the 60 and see, because the frequency terahertz goes, a lot of things changes. So that you explore first. After that, you can apply this machine learning part. Okay.
Okay, sir. Thank you very much, sir.
Okay. So any other questions?
Yes, sir. So in what all the technology now we want to do any implementation in research work means we want to apply machine learning only is a super will give the uh, superior result in everything. Whatever the
No,
approach we
no,
want to do, we want to implement in machine
no.
learning.
There, no. The trend is, that is what the trend is. See, I have to tell you the honestly things. So now the world is moving towards the ML, the processing side, data processing, artificial intelligence, and you know very well, a lot of IITs and a lot of institutes in India started BTech program in artificial intelligence, and almost many people have, many people in the sense, many institutes have launched artificial intelligence is master's level. I'm taking care of the CCMP. I know that many institutes in India have degrees in artificial intelligence, machine learning, artificial intelligence. The country is marching, and the government of India also a lot of projects on AI, and they support huge amount of funding in AI. So the country is marching towards AI. So therefore, it is good to work on AI. But the solutions, the second part of the question is, will the ML will solve everything? Will it apply to all the areas? No. ML is an where the concrete analytical models were not available. Whenever the concrete analytical models were not available, then you can apply ML solution. Okay, when the data is available, concrete conventional concrete solutions are not working. That means the conventional mathematical models are not working. Then you can just, for example, undersea communication, underwater communication, or undersea communication. This, NIOT in India, National Institute of Ocean Technology, they survey about the sea wave and tides, everything, right? The sonar signals which you get. There you can apply machine learning because you will get lot amount of data from the Indian at shipyard, and they supply a lot of data, and from this NIOT you can get that data, then you can analyze that. That's such places you can apply this. And you can apply email processing, surveillance, all these things wherever the data are available. But when it comes to the communication side, what is happening? We just transmit signals waveform. And conventionally, this is communication is a century-old subject, and lot of built system, already built systems are available. Solutions are available like ML decoding, MMSC, 0% MMSC. Lot of things are already available to handle the randomness of the channel, randomness of the data. Therefore, the role of ML is limited, but still, if we explore to handle the data fluctuations, then it is well and good. Okay, and therefore, the one line is the ML can be applied, ML AI can be applied for the suitable areas.
Okay, thank you, sir.
Good afternoon, sir.
Yes.
Sir, what's the difference between subcarrier and subchannel, sir? Because you told about a subcarrier can.
Yeah, same in YFDMA we're asking, it is same.
Okay,
Subchannel
sir.
only, I'm just calling this a subcarrier.
So subchannel and subcarrier both are same terms.
Yeah. The carrier is, we generally suppose what is channel and what is carrier is, the carrier is, we just say that one frequency. It's a single tone. Single tone means only one frequency. For example, if I write AC cos 2 pi FCT plus I is the phase. So this is a single tone. So this is, we call it as a carrier. But a channel means a band of frequency. That is called channel. Okay, so the difference between the carrier and channel is, carrier means single frequency, channel means a band of frequencies. That is the difference. But
Okay.
in YFDMA case, they just interchangeably use it. 64 subcarriers they say, 64 subchannels they say. It's all fine. It's all within the same thing only. The channel will have one carrier frequency, one center frequency of the channel. We call it as a carrier frequency.
Okay. Thank you, sir.
Sir, good afternoon, sir.
Yes.
Sir, I'm Janardhan.
Yes.
My question is, it is a general question.
Yes.
Sir, we are doing a number of researches, more articles coming in respect of 5G, 4G and all. Still our data rate is very poor when compared to other countries. we are in the bottom of the list. Our BSNL not even able to implement a 4G yet, even in the major cities. What we can do in order to improvise the data rate, because recently I have read an article that Japanese having in a fixed landline network, their internet speed is up to 319 terabits per second. But still in India, in a fixed landline itself, we are struggling. Average internet speed is only 70 Mbps.
Yes.
As a academician, as a technician, what way we can contribute or instrumental in bringing the internet speed up, sir.
Yeah.
And also we are finding that lot of fluctuations in the available internet speed itself. So morning one data rate, and afternoon another data rate, and evening another speed, like that it is coming, sir. What we can do, sir?
Yeah. So there are two things I want to explain. Maybe one small light note, because you asked a very good question. One light note.
Thank you, sir.
Yeah, yeah. Fine.
Thank you, sir.
So suppose everybody can manufacture chips, right? Chips means I'm just telling eating chips, the potato chips. Everybody can manufacture. There are two things. One is manufacturing, another one is selling, business. But all the vendors cannot successfully sell chips, potato chips, right? Only two, three vendors only can dominate a large market and sell a lot of chips, potato chips. So why it is possible is because the manufacturing is different, business is different. Everybody can make cinema. That is a manufacturing. They can take a good artistic, the directors who has a good, creativity and artistic skills can create a movie. But the second part is the business part. The producers who should be also efficient to make a good business out of it. Right? So that means manufacturing is by the director and the business is done by the producer. The producer, director both should be efficient, then only the content will reach all. So therefore, there are two things. The technologists who work for this developing technologies, they are all the manufacturing side, and everybody contributes a lot. Of first thing is the research level. The academicians will contribute the theoretical ideas and a small part of the experimentation results. Everything they will contribute. And based on the contributions of the academic community, and the industry also does a research R&D, and they also contribute. So finally, a forum is formed, a standardization committee is formed to get the inputs from the academic media plus industries. Everybody put together, have a joint committee, and they go for standardization. And all the vendors agree to follow the standard for the particular thing. But when the standardization comes, the business comes. The moment till standardization, it is the academic part, research part, whatever we speak, all that. But once the standardization to the bringing that product to the market, 5G standardization to the bringing the market product to the market is a business part. But for the business part, there are two things. One is you need large number of customers. A country like India is marching very faster. It is not like we are lagging, but initially we were lagging. Now this 5G, 4G and all, we have a huge number of subscribers. I think today morning, Dr. Priyanka Kokil said Troy said, I think 130 millions, 130 crore people in India are using the mobile phone. We may be 140 or 150 total population. She was telling that statistics we have to check, but still 100 crore people maybe definitely will be having a mobile phones in India. Their connectivity everywhere you can see people without mobile phone you cannot find. But when the technology pickup is contained, people cannot take it. Say, unless the technology is provided to you, cannot take. Almost all the cities nowadays they are getting 4G connections. If not BSNL, there are many vendors. BSNL is also providing excellent service in cities. But if not BSNL, there are other competitive vendors are also there. So the Troy is playing, the Troy is placing a significant role to do that. And we have, the government of India also very closely watching how to bring this 5G to India as fast as possible. But there are countries who are people are rich and the country itself smaller, and bringing any technological changes is very easy. See, you purchase a 4G mobile phone. And the moment 5G comes, you have to change your mobile phone. So it is like, just think the people have to throw the mobile phone, go for a new mobile phone, because the new mobile phone is going to have lot more, options, lot more technique things. We are ready to embrace the technology, but it is at the cost of economy, right? So, you know, there are many business things are available. That is why it is going in a phased manner. But it is a need of the hour. Nobody can stop technology. See, technology cannot be stopped by anything. The change you cannot. Nobody can stop. So all the countries will embrace 5G and the forthcoming 6G, and they adapt it. And countries like India is in a fast-moving way. Definitely, we are going to have the 5G soon. The market maybe actually it was planned. Honestly speaking, the mid 2020, it's 2021 itself. It was planned. I think if you read the magazines, all that you may know that. But because of the corona in the last 2 years, and I think this entire 5G things has got delayed. Country were focusing on other things. Everyone, the entire world is focusing on that. Therefore, it has got totally, the business was down. And maybe it will pick up in the next year. Definitely by next year we will get all 5G. Okay. So let me, any other quick questions?
So thanks for the reasonable answer, sir.
Yes, thank you.
We have to accept the other side also. We are a bigger country compared to other nations. Number of subscribers are huge. So adapting new technology is a big issue. Thank you, sir.
Yes, sir.